Great ideas power progress. Welcome to CAD017_Learn, where we connect circuits to cranes and explain the industrial world.
A modern, multi-lane city intersection managing hundreds of vehicles every hour is a true masterclass in precisely controlled timing. Today, we are going to engineer the logic for an automated dual-lane traffic light system from scratch using the PIC16F877A microcontroller. The core challenge of embedded engineering is translation. Microcontrollers process abstract C code and memory addresses, but real-world hardware, like traffic LEDs, requires physical changes in electrical voltage. The microcontroller acts as the physical bridge. It reads sequential programming instructions and translates them into electrical currents, routing voltage out of specific microscopic pins on the chip. To safely manage an intersection, we have to organize these voltage changes into a deterministic finite state machine, a closed-loop system of strict predictable phases. This process, mapping logical memory states to physical electrical potential, is the mechanism that allows software to interact with the physical world. This diagram outlines the physical layout of the bare metal PIC16F877A microcontroller. On the right side, notice this distinct cluster of pins labeled Port B. Before we write a single line of software, we must strictly map the physical wiring for our two traffic lanes to these specific hardware pins. For lane 1, we map the red, orange, and green LEDs directly to pins RB0, RB1, and RB2. Lane 2 mirrors this setup on the higher pins, with its red, orange, and green LEDs tied to RB5, RB6, and RB7. Notice the deliberate gap left at pins RB3 and RB4. This highlights a crucial hardware feature. Every single pin on this port is independently targetable. We must place current-limiting resistors in series with each LED. Without them, the moment a pin outputs 5 volts, the LED would fail. To keep the entire system synchronized, we introduce a central heartbeat, an external 8 MHz crystal oscillator. This component connects directly to the dedicated OSC pins on the chip. It generates the strict, repeating clock cycles the internal processor needs to execute commands at exact intervals. But at this stage, these physical wires are inert. There is no voltage flowing because the silicon gates don't yet know when to send current. Routing the external circuit is only half the engineering process. We now have to program the internal memory registers to align with these physical pathways. Inside the microcontroller, right behind those physical pins, sit two 8-bit memory blocks, the TRIS-B and Port B registers. This diagram shows how they map directly to the hardware. The TRIS register, short for tri-state, acts as the system's gatekeeper. Its sole job is to determine the direction of data flow for each pin. The universal rule for TRIS configuration is simple. Setting a specific bit to 1 turns the corresponding pin into an input. Clearing the bit to 0 forces the pin to act as an output. Since our traffic LEDs only receive voltage and don't send data back, we must explicitly configure the entire TRIS-B block as an output line. We do this with a single hexadecimal initialization command in our C code, TRIS-B equals 0x00. With the direction firmly set, we move to the Port B register. If TRIS dictates which way the traffic moves, Port B acts as the switchboard that controls the electrical state, whether a pin sits at high or low voltage. Writing a binary 1 into a specific slot in the Port B register immediately forces 5 volts out of the corresponding physical pin, illuminating the connected LED. Overwriting that same slot with a binary 0 cuts the voltage, turning the LED off. By separating the data direction in TRIS from the electrical state in CORT, the architecture provides engineers with deterministic control over every output. This technical flowchart maps our physical hardware into a sequence of behavioral states. We read it from the top down. The initial default state of the intersection requires lane 1 to hold its red LED on, while lane 2 has the right of way with its green LED on. The logic dictates that this exact hardware state must be held static for a strict time period, represented here as 30 seconds, to allow traffic to flow. Next comes the transition phase. Lane 2 drops its green light and activates the yellow LED, creating a warning period before the intersection changes. Once the warning phase ends, the microcontroller fires the mirrored secondary state. Lane 2 locks it red, and lane 1 is permitted to go green. At the bottom of the diagram, a feedback loop routes the execution path all the way back to the start, locking the sequence into a cycle. Implementing this closed-loop flowchart in software converts a set of unconnected components into an autonomous traffic management system. Now we look at the actual C firmware written to execute that logic on the PIC chip. This split view shows the code alongside the hardware controls. At the top of the file, we use #define compiler macros to assign physical connections, like defining red1 to equal pin RB0. These macros allow the programmer to command the hardware using logical, human-readable labels instead of raw memory addresses. Entering the infinite while 1 loop, we trigger the first intersection state. The code assigns a binary 1 to red 1 and green 2, and a 0 to the other components. Immediately following those state changes, we hit a command for the millisecond delay macro. In embedded programming, a delay function forces the central processing unit to freeze its instruction execution, calculating the pause by counting the physical cycles of the 8 MHz oscillator. By halting the processor, the microcontroller maintains the existing high and low voltages on the port B pins for exactly 5,000 milliseconds. This sequence, toggling specific memory registers followed by hardware-enforced delays, forms the fundamental rhythm of embedded procedural control. Looking at the complete pipeline, the architecture of the system is clear. We abstracted the hardware pins into macros, locked the data direction using the tris register, and commanded physical voltage states using port manipulations and clock delays. While blinking 5-volt LEDs on a laboratory breadboard is a straightforward visual aid, this exact same microcontroller architecture scales directly to heavy industrial applications. Instead of connecting a tiny light-emitting diode, you can connect the output pin to a 5-volt electromagnetic relay module. Pushing a 1 to that port pin now triggers the relay coil, allowing the system to switch 230-volt alternating current loads. This means the chip can drive heavy industrial motors or actual municipal streetlights. The C firmware, the tris initialization sequence, and the state machine logic remain completely identical, regardless of the size of the physical payload. Navigating the memory-mapped architecture of a microcontroller provides the framework used to automate control systems across the physical world.
Let's study more, and like, share, and subscribe for such more content, and comment something you want to learn.